The surface of the Pacific Ocean, directly above the deepest point on Earth, is warm. On a clear day, it sits near 28 degrees Celsius, a tropical blue, sun-warmed from above, wide and unremarkable to look at from a ship's deck. Nothing visible at the waterline suggests what lies below. The water is the same color it is 1,000 kilometers in any direction. Seabirds cross it. Wind moves across it in low, gentle corrugations, and straight down, below the keel of any vessel that passes overhead, the ocean floor sits at 10,935 meters, nearly 11 kilometers of cold, pressurized, lightless water between that warm surface and the sediment at the bottom of the deepest trench ever measured on this planet. The distance is worth staying with for a moment. 11 kilometers is a meaningful length on land. It takes roughly 2 hours to walk 11 kilometers at a comfortable pace. Mount Everest, the tallest point on Earth's surface, rises to a little under 9 kilometers above sea level. The depth of Challenger Deep exceeds it by more than 2 kilometers. If Everest were placed at the bottom of the Mariana Trench and submerged entirely, its summit would still rest more than a mile below the ocean surface, with open water above it in every direction. The trench does not look like anything from the outside. It is simply a region of the ocean where the floor has been pulled very far down, and the water above it has filled the space entirely, and the result is a column of ocean almost twice the height of any mountain range on land. The place has a name, and the name is specific. Challenger Deep is the deepest surveyed point within the Mariana Trench, a distinct depression within a larger depression, sitting at approximately 11 degrees north latitude and 142 degrees east longitude, roughly 300 kilometers southwest of the island of Guam. The coordinates place it in the western Pacific, in a region of ocean that is not particularly trafficked, not particularly close to anything on land, and not visible in any meaningful way from the surface. A ship can sit directly above it and know, from its instruments, that the floor is nearly 11 kilometers below, and the ocean looks exactly the same as it does anywhere else. The depth was confirmed to its current precision by a survey completed in 2010, conducted by the United States Centers for Coastal and Ocean Mapping, using multi-beam sonar, a technology that sends sound pulses downward in a wide fan and measures the time it takes for each pulse to return after bouncing off the seafloor. The survey placed Challenger Deep at 10,935 meters below sea level, a figure that represents the deepest point yet confirmed by direct measurement anywhere on Earth. The number is precise in the way scientific measurements are precise, arrived at through careful instrumentation, peer review, and the understanding that future surveys with improved equipment may refine it slightly. For now, it stands as the best available answer to the question of how deep the deepest place is. The Mariana Trench itself is older and larger than any single measurement of its deepest point can convey. It formed and continues to exist because of a process occurring at the boundary between two enormous sections of the Earth's outer shell, the Pacific Plate and the smaller Mariana Plate. Where these two plates meet, the Pacific Plate is moving westward and downward, pressing beneath the edge of the Mariana Plate and sinking into the hot mantle beneath. The rate of this convergence is approximately 2 to 3 centimeters per year. That is roughly the speed at which a human fingernail grows, a pace that feels almost imperceptibly slow when stated as a number, and yet over millions of years it has been enough to bend the ocean crust downward along the line of contact into an elongated, arc-shaped depression stretching more than 2,500 kilometers across the western Pacific floor. The bending happens because the subducting plate pulls the ocean floor downward at the point of collision, creating a flexure in the crust, a long crescent-shaped sag that deepens wherever the subducting slab has pulled hardest and longest. The Mariana Trench is the result of that flexure, and Challenger Deep is its deepest expression, the point where the floor has been pulled furthest from the surface, where the downward pressure of the subducting plate has been most sustained over geological time. The whole structure is not static. The Pacific Plate is still moving. The flexure is still occurring. The trench is, in the most literal sense, still being made, very slowly, in geological increments, at the speed of a growing fingernail. The Pacific Plate covers more of the Earth's surface than any other single tectonic plate. It stretches from the western coast of North America across to the margins of Asia and Australia, an area of ocean floor measuring tens of millions of square kilometers, all of it moving as a single rigid unit at the unhurried pace of tectonic drift. Along its western and southwestern edges, where it encounters island arc systems like the Mariana Islands, it subducts, angles downward into the mantle, and is consumed. The Mariana Trench runs along this boundary for approximately 2,550 kilometers, curving in a gentle crescent that follows the line of subduction across the ocean floor. That length, roughly equivalent to the distance across the contiguous United States from the Atlantic coast to the line of the Appalachian Mountains, is the full extent of the trench system as a whole. Challenger Deep is simply the deepest part of it, a specific low point within a much longer depression. What the subducting Pacific Plate produces, beyond the trench itself, can be seen in the geography of the region. To the east of the Mariana Trench, running roughly parallel to its length, sits a chain of underwater volcanoes collectively known as the Mariana Arc. These volcanoes exist because of the same geological process that created the trench. As the Pacific Plate sinks into the mantle beneath the Mariana Plate, the heat and pressure at depth cause water and other volatile compounds locked within the subducting rock to be released. Those released volatiles lower the melting point of the mantle rock above, generating magma that rises through the overriding plate and erupts at the sea floor. The result is a line of underwater volcanoes, some active, some dormant, running alongside the trench in permanent geological relationship with it. Where the trench descends, the volcanic arc rises. One is the direct consequence of the other. Descending from the warm surface water above Challenger Deep, the first significant physical change a diver or instrument would encounter is not pressure, but temperature. The surface layer of the tropical Pacific, heated by sunlight, holds near 28 degrees Celsius for its uppermost 100 meters or so. Below that, within a zone called the thermocline, temperature drops steeply, falling from the warm surface layer through progressively cooler water as depth increases. By around 1,000 meters, the water temperature has dropped to near freezing. The change across that first kilometer of depth is sharp enough to be measurable in very small increments of distance. The temperature gradient is steep and consistent wherever warm tropical surface waters overlie cold, deep water. Below 1,000 meters, the descent levels off. The water at 2,000 meters is cold. The water at 5,000 meters is cold in nearly the same way. The water at 10,000 meters, 9 kilometers deeper, has changed very little in temperature since the 1,000 meter mark. This near constant cold of the deep ocean is one of its defining physical features. Water at Haddle depths, the zone between 6,000 and 11,000 meters, typically holds between 1 and 4 degrees Celsius. The specific temperature varies slightly by location and depth, but the range is narrow. The reason is insulation. The kilometers of cold, dense, largely still water sitting above the Haddle zone suppress any meaningful heat exchange with the sun-warmed surface layer. The surface of the Pacific heats and cools with the seasons, with the time of day, with cloud cover and wind. None of those variations reach the floor of Challenger Deep in any measurable way. The bottom of the trench exists at a temperature that has been stable, in a practical sense, for longer than human civilization has existed, somewhere in the narrow band between 1 and 4 degrees, cold and still and dark. Pressure at those depths is the condition that most distinguishes the Hadal zone from any environment accessible to ordinary human experience. At the surface of the ocean, the weight of the atmosphere above presses down at approximately 14.5 pounds per square inch, what is called 1 atmosphere. With every 10 meters of descent into the ocean, the weight of the water column above adds another atmosphere of pressure. At Challenger Deep, the accumulated weight of nearly 11 kilometers of seawater above produces a pressure of approximately 15,750 pounds per square inch. That is roughly 1,086 atmospheres, more than 1,000 times the pressure at sea level, bearing down equally in every direction on everything that exists at that depth. The pressure is not experienced as a force acting from outside inward in the way that a crushing weight might be imagined to press. It acts equally in all directions simultaneously, from above, from below, from every side at once. Objects that contain gas-filled spaces compress under that equal pressure because gas is compressible in ways that water and most solids are not. A sealed air-filled container brought to Hadal depth would be crushed by the imbalance between the pressure outside and the atmospheric pressure of the air trapped within. But water itself is nearly incompressible, and organisms whose bodies are composed primarily of water and solid biological material, without significant gas cavities, can exist at those pressures with different challenges than simple mechanical crushing. The adaptation required is chemical rather than structural. The molecules inside living cells must be able to function at pressures that would disrupt or denature them at the surface. The life that exists at Challenger Deep has, over evolutionary time, found ways to manage this. The pressure is simply the condition of the place, as ordinary to its inhabitants as sea level is to the organisms that live there. To give the pressure a concrete scale, the commonly cited comparison involves the weight of jumbo jet aircraft. At the pressure of Challenger Deep, approximately 15,750 pounds press down on each square inch of surface area. Spread across 1 square meter, about 10,500 square inches, that is a total force equivalent to the weight of roughly 50 fully loaded jumbo jets pressing down simultaneously. The comparison is, like all such comparisons, imperfect. The pressure at Challenger Deep does not feel like 50 jets because it acts from every direction equally rather than from above only. It is more useful, perhaps, simply as a way of grasping that the number involved is very large, and that the physical conditions at the deepest point in the ocean are removed from anything a human body at the surface experiences by an enormous margin. The year 1875 is where the measured history of the Mariana Trench begins, in a sense that can be documented. HMS Challenger, a British Royal Navy corvette that had been converted and specially equipped for oceanic research, was conducting the first global systematic survey of the ocean floor, crossing the Pacific in a circuit that would take more than 3 years and cover nearly 70,000 nautical miles. The ship's scientists were measuring ocean depths by lowering a hemp line with a weight at its end over the side, counting the line as it paid out, and recording the length when the weight met the bottom and the tension went slack. Most soundings came back with depths of a few thousand meters. In March of 1875, In the western Pacific Southwest of the Mariana Islands, the line was paid out to 4,475 fathoms before it went slack, a depth of approximately 8,184 meters. The measurement was recorded in the ship's log. It was unlike anything the expedition had measured before in the ocean, and it named the region of interest that would occupy oceanographers for the next century and a half. That weighted hemp line, paid out by hand in bright Pacific sunlight from the deck of a 19th century sailing ship, was the first instrument to touch the question of how deep the Mariana Trench was. The crew could not have known, lowering it, that the line was settling toward a feature of the ocean floor produced by the convergence of tectonic plates, a concept that would not exist in science for another 90 years. What they knew was that the line had gone very far down before going slack, and that the ocean was, at that location, deeper than they had found it anywhere else on their survey. The hemp line eventually became a multi-beam sonar survey. The figure of 4,475 fathoms eventually became 10,935 meters. The process of refinement has been ongoing since 1875 and continues today. The full trench system that the 2010 sonar survey mapped in its most complete form stretches, as noted, approximately 2,550 kilometers in a gentle crescent arc across the western Pacific floor. Its width varies, but averages around 69 kilometers across. Its depth varies considerably along its length. Most of the trench floor sits far shallower than Challenger Deep, but at its deepest point, in the southwestern portion of the system, the floor drops past 10,000 meters in a region that closer examination has revealed to contain not one deep basin, but three distinct ones, each one pressing below the 10,900 meter mark, and each one separated from the others by slightly shallower saddles in the seafloor topography. These three subbasins within Challenger Deep are referred to informally as the Eastern, Central, and Western pools. The names correspond loosely to their positions along the length of the feature, though the geography is subtle enough that without the high-resolution sonar data gathered in 2010 and subsequent surveys, the distinctness of the three basins was not fully apparent. Each of the three independently exceeds 10,900 meters in depth. The deepest point yet measured, the figure of 10,935 meters, falls within one of these basins. The others are close behind. The structure is not a simple bowl or a single pit. Looking at Challenger Deep in 3 dimensions, as the sonar data allows, the impression is of a complex seafloor landscape of depressions within depressions, ridges and slopes, and abyssal plains, all present at a scale of meters and tens of meters, rendered in detail by the careful analysis of sound waves sent and received across 11 kilometers of cold water. The three pools sit side by side along the axis of the trench, their floors individually mapped to resolutions that allow the contours of each basin to be distinguished from its neighbors. Between them, the seafloor rises slightly, not to anything that could be called a ridge or a reef in any ordinary sense, but enough to create three structurally distinct depressions within what is already the deepest region of ocean anywhere on Earth. The ocean above these three pools is unbroken. Looking down from the surface, there is nothing to see, no disturbance, no color, no visual marker. The water is blue from above and black from within, and entirely unremarkable from any angle visible to the unaided eye. Below the surface layer, through the thermocline, through the cold intermediate water, through the deep ocean and the abyssal zone, and into the Haddle depths below 6,000 meters, the water becomes progressively more still, more uniform in temperature, more completely dark, The last trace of sunlight penetrates to perhaps 1,000 meters under ideal conditions. Below that, the ocean holds no light that originates at the surface. The deepest 5 kilometers of water above Challenger Deep are lightless, not dim, not twilight, but the complete and persistent absence of any solar illumination. That condition has been consistent at the floor of the trench through every season, across every year, for longer than the trench itself is measurable in human terms. The geological age of the Mariana Trench, as a feature of the ocean floor, is measured in tens of millions of years. The Pacific Plate has been subducting beneath the Mariana Plate for long enough that the arc of the trench has shifted, deepened, and been shaped by geological forces operating across timescales that resist any meaningful comparison to human experience. The current configuration of the trench, its length, its curvature, its depth at Challenger Deep, represents a particular moment in a process that has been ongoing since before most modern ocean basins existed in their current form. The measurements taken in 2010 are a snapshot of a structure that is, by geological standards, still in the process of forming. This is a feature of the place worth sitting with. The subduction is still happening. The Pacific Plate is still moving westward and downward at 2 to 3 centimeters per year. The floor of the trench is not a fixed geological fact any more than the height of a mountain is fixed. It is the current result of a continuing process, subject to change over geological timescales in ways that no sonar survey can capture. The trench that exists today is the trench produced by every millimeter of subduction that has occurred up to this point. The trench that will exist in 10 million years will be the product of everything that comes after. The shape of the floor, the eastern pool, the central pool, the western pool, each one dropping past 10,900 meters, records the history of the subducting plate in the accumulated geometry of the depression it has produced. A ship sitting on the surface above Challenger Deep would record on its instruments a depth of 10,935 meters below its keel to the nearest confirmed point on the sea floor. The water beneath it would be 28 degrees warm in the uppermost layer, cooling through the thermocline to near freezing by a kilometer down, and then holding that cold, steady, stable, dark for the remaining 10 kilometers to the floor. The pressure at the bottom would be 1,086 atmospheres. The temperature would be somewhere between 1 and 4 degrees Celsius. The floor itself, mapped in 2010 by sound waves and rendered in 3 dimensions, would consist of 3 distinct basins, each one independently deeper than any other feature in the ocean outside this region, each one quietly present in its mapped position on the seafloor. The eastern pool sits at the far end of the trio as the trench curves toward the northeast. The central pool is the one whose floor contains the deepest confirmed point yet measured. The western pool extends toward the south and west, its own floor pressing past 10,900 meters in its own basin, independently deep, structurally distinct. Between them, the saddles of slightly shallower seafloor mark the divisions, subtle in absolute terms, significant in the geography of a place where meters of difference matter for how deep a depression reaches. The 3 basins together compose the full extent of what is called Challenger Deep, a feature named for a ship that first sounded near this region with a weighted line in 1875, and which has been measured with increasing precision in the century and a half since. The trench does not announce itself. Nothing about the surface of the Pacific at that location marks the seafloor below as different from the seafloor at any other point in the western Pacific basin. The surface is warm and blue and open. The seabirds crossing it have no instruments. The wind does not slow. The water looks the same as it does 1,000 kilometers away, where the ocean floor sits at 5 or 6 kilometers of depth rather than 11. The extremity of the place is entirely internal, embedded in the column of water between the surface and the floor, accumulating downward through pressure and cold and darkness into the three quiet basins that sit at the deepest point on Earth, each one resting in the dark below 10,900 meters, each one mapped and named and precisely located, each one entirely still. The warm surface water above is 28 degrees. The cold bottom water rests near 2 degrees. Between them is almost 11 kilometers of ocean, and at the bottom of that ocean, 3 basins sit in the positions the sonar survey recorded: the eastern pool, the central pool, the western pool, each one holding its place in the dark at a depth that has no parallel anywhere else on Earth, resting at the bottom of a trench still in the slow geological process of becoming deeper in a part of the Pacific that looks from above like any other part of the Pacific and is unlike it in every way that a measurement can capture. The floor of the 3 pools is pale sediment, arrived at through long accumulation, marine snow, the slow fall of organic particles from the surface world above, gathered over time into layers on the seafloor. At the surface, warm light. At 1,000 meters, cold and dark. At 10,900 meters, the 3 basins of Challenger Deep, each one independently exceeding a depth that nothing else on this planet can match, their floors covered in the same pale sediment, their water near 2 degrees Celsius, their pressure more than 1,000 atmospheres, their structure mapped in 3 dimensions from the acoustic returns of sound pulses sent downward through 11 kilometers of ocean in 2010. The eastern pool, the central pool, the western pool, 3 depressions within a depression, within a trench, within an ocean, sitting in their positions on the seafloor in the cold and the dark, beneath 11 kilometers of Pacific water, 300 kilometers southwest of Guam, as quietly structured as anything on Earth has ever been. On January 23, 1960, the bathyscaphe Trieste sat on the floor of Challenger Deep with 2 men inside it. The descent had taken 4 hours and 47 minutes. Outside the thick viewport of the steel observation sphere, the water was completely dark, and the temperature was just above freezing, and the pressure against every surface of the vessel was equivalent to more than 1,000 times the weight of the atmosphere at sea level. Jacques Piccard and Don Walsh had arrived at the deepest point any human being had ever reached, and they spent approximately 20 minutes there, looking out at a sediment floor that no eye, human or otherwise capable of reporting back, had ever seen before. The observation sphere they occupied was small. Its interior was roughly the size of a compact car's passenger compartment. 2 men, their instruments, their breathing equipment, and the viewport through which they watched the outside world. The Trieste itself was a bathyscaphe, a design quite different from a submarine. Above the sphere hung a large float tank, filled not with air, but with aviation gasoline, which is lighter than seawater and provided the vessel's buoyancy. Steel-shot ballast held it down on the descent. To ascend, the crew released the shot, and the gasoline lifted the whole assembly back toward the surface. The engineering was methodical and deliberate, built from principles that had been worked out over the previous decade by Auguste Piccard, Jacques' father, who had designed the vessel and had himself made deep dives in earlier bathyscaphs in the Mediterranean and the Atlantic. What Piccard and Walsh saw through the viewport during those 20 minutes on the bottom was, by their account, a flat, pale sediment surface extending into darkness beyond the reach of the vehicle's lights. The sediment was soft and undisturbed looking, Walsh later described the floor as covered in a kind of diatomaceous ooze, fine material accumulated over very long periods, drifting down from the water column above. Picard reported seeing a small flatfish near the vehicle, a sighting that has been discussed and questioned ever since, because the pressure at that depth was thought by some researchers to be inconsistent with the physiology of bony fish. The identity of the animal, whether it was a fish or perhaps a sea cucumber or holothurian of some kind, was never definitively established from the available record. What remained beyond question was that something was moving on the floor of Challenger Deep in the lights of the only vessel ever to have reached it with a human crew at that point in history. The ascent took 3 hours and 15 minutes. The Trieste rose through the same column of water it had descended through, passing back through zones of increasing light, the deep black of the Hadal zone giving way, over many thousands of meters, to the faint blue-gray of the mesopelagic, then to the warmer blue of the epipelagic, and finally breaking the surface in the tropical Pacific in the early afternoon. Walsh later said that the moment of surfacing felt less like an arrival than a return, the ocean simply becoming the ocean again after the hours of darkness below. The descent of the Trieste had been preceded by nearly a century of growing understanding of what might lie beneath the surface of the Pacific in that region. In March of 1875, the crew of HMS Challenger, a Royal Navy corvette that had been converted for scientific survey work and set out from Portsmouth in December 1872 on a voyage that would last more than 3 years and cover approximately 130,000 kilometers, took a sounding in the Western Pacific that returned a depth unlike any they had recorded before. The method was direct and slow. A weighted hemp line was paid out over the side of the vessel by hand, unreeling from spools on deck into water that was warm and blue at the surface and entirely unknown below. When the line finally went slack, the recorded depth was 4,475 fathoms, a measurement that converted to modern units corresponds to approximately 8,184 meters, which is considerably shallower than the confirmed depth of Challenger Deep, but was in 1875 the deepest sounding taken anywhere in the ocean. The crew feeding that line over the rail would have worked in bright Pacific sunlight, watching the hemp pay out for a very long time, long enough that the act of measuring became its own kind of patience, a slow unwinding of attention as the line descended through water that was from the deck simply invisible. When the weight finally hit bottom and the line went slack, the number they read off the marks on the line was not a number any of them had encountered before. The region they had been sampling was named for the vessel afterward, and the specific depth within it, found by later surveys with more precise instruments, took the vessel's name as well. Between 1875 and 1960, a series of additional soundings refined the understanding of the trench's depth. In 1951, HMS Challenger II, a different vessel, named in deliberate reference to the original, took a sounding in the same region using echo sounding technology and returned a depth of approximately 10,900 meters, the first measurement close to what would be confirmed by later surveys. It was this sounding that gave Challenger Deep its name, fixing the location as the deepest known point in the ocean and setting the target that the Trieste expedition 8 years later would attempt to reach. The progression from hemp line to echo sounder to submersible took less than a century, which is, measured against the age of the trench itself, an interval too brief to register as anything other than instantaneous. After the trench's dive in 1960, the floor of Challenger Deep was not visited again by any vehicle, manned or unmanned, For 35 years, the technology of deep-sea exploration was developing during that period, but the engineering challenges of reaching full Hadal depth remained substantial. The trench was studied by acoustic survey, by sediment cores retrieved on long wires, by the samples and recordings made during the Trieste dive itself. What was missing was direct observation of the floor, the ability to send a camera and a sensor package to the very bottom and retrieve both the data and the equipment intact. That capability arrived in March of 1995, when the Japanese remotely operated vehicle, Kaiko, descended to the floor of Challenger Deep and reached a depth of approximately 10,911 meters. Kaiko was a large vehicle by the standards of the time, roughly the size of a small car, built to withstand the pressure of full Hadal depth, connected to its support ship by a fiber optic tether through which data and video flowed continuously during the dive. It descended alone through the full column of water that the Trieste had passed through 35 years earlier, its camera lights on, its sensors recording. When it reached the bottom, it collected sediment samples and biological material from the surface of the floor, and then it ascended and was recovered by the ship above. The footage and samples Kaiko returned changed what researchers knew about the floor of Challenger Deep. The sediment surface was visible on camera in a way it had never been before, not the brief glimpse through a small viewport that Picard and Walsh had managed, but a sustained, directed recording from a vehicle that could be steered across the bottom. Organisms were visible. The sediment had texture and variation. The samples, once analyzed in laboratories, revealed microbial communities and small fauna living in the ooze at the deepest point in the ocean. Kaiko continued to make dives in subsequent years, returning to Challenger Deep and to other deep-sea locations around the Pacific, until it was lost at sea in May of 2003, when its tether was severed during rough weather. The vehicle still attached to the secondary cable, both pieces disappearing before the ship's crew could recover them. The loss of Kaiko left Japan without a full-depth capable vehicle for several years. The engineering work of replacing it took time. In the interval between Kaiko's loss and the construction of its successor, another opportunity to reach the bottom of Challenger Deep with a direct observation platform came from an unexpected direction. On March 26, 2012, James Cameron descended to the floor of Challenger Deep in a vehicle called the Deep Sea Challenger, a vertically oriented submersible, quite different in design from the Trieste or from conventional ROV systems, built over several years in collaboration with engineers in Australia and designed specifically for a single solo dive to full ocean depth. The descent took 2 hours and 36 minutes. Cameron reached the bottom at 10,908 meters and spent approximately 3 hours on the seafloor, piloting the vehicle across the sediment surface, operating scientific instruments, and recording footage with cameras designed to function under extreme pressure. The landscape Cameron described afterward was, in his words, lunar-like, a pale, flat sediment surface with very little visible relief, extending in every direction beyond the reach of the vehicle's lights. The sediment was fine and soft, and the vehicle's thruster wash disturbed it easily. Cameron noted the presence of small organisms, shrimp-like creatures among them, but the primary focus of the dive from a scientific standpoint was the collection of sediment samples and the recording of environmental data that could be retrieved and analyzed after the vehicle surfaced. The dive lasted long enough that Cameron was able to traverse a meaningful portion of the immediate area around the landing point and return data that complemented what Kaiko had gathered in the years before. One image from the 2012 dive became well known after Cameron's return, a plastic bag visible on the floor of Challenger Deep, resting undisturbed on the sediment surface at more than 10,000 meters of depth. The bag was intact. Its origin was somewhere on a land surface or on the ocean surface, a very long time before the cameras recorded it. Its presence on the floor of Challenger Deep was not something that required explanation beyond the basic physical fact that the ocean is connected to everything that enters it, and that material which sinks tends, eventually, to find the lowest available point. Cameron donated the Deep-Sea Challenger to the Scripps Institution of Oceanography after the dive, where it became part of the institution's collection. What Cameron's dive added to the human understanding of Challenger Deep was not primarily a new depth record. The Trieste had reached the floor in 1960, and Keiko had returned with physical samples, but rather a period of sustained, directed observation by a human pilot with the ability to make real-time decisions about where to go and what to document. The 3 hours Cameron spent on the floor of Challenger Deep were longer than any previous human presence there by a wide margin. The data collected during that time, combined with what Keiko's dives had produced, gave researchers a richer picture of the floor than had previously existed. The Deep-Sea Challenger dive was also significant in making visible, to a much wider public, the existence of the trench as a specific visitable place rather than an abstract depth on a chart. Cameron was a known figure, and the dive was followed in real time by a substantial audience. The footage released afterward was widely circulated. The effect of this visibility was, among other things, an increase in public attention to what the trench contained and what it might mean that human materials were already resting on its floor. The plastic bag on the sediment was not hidden in a technical report. It was in the footage. The next significant development in the direct exploration of Challenger Deep came from a different kind of program altogether. The 5 Deeps expedition, conducted in 2019 and privately funded by the American businessman Victor Vescovo, had the explicit goal of reaching the deepest point in each of the world's 5 oceans. The vehicle used for the expedition was the DSV Limiting Factor, a 2-person submersible built by the company Triton Submarines specifically for the project, designed to make repeated dives to full ocean depth without requiring major rebuilding or maintenance between descents. The DSV Limiting Factor reached the floor of Challenger Deep in May of 2019, carrying Victor Vescovo on the first dive. It returned to the bottom multiple times during the expedition with Vescovo, and subsequently with scientists and other passengers, including Don Walsh, who thus became the first person to return to Challenger Deep after the 1960 Trieste dive. The vehicle's ability to make repeated dives was central to what the expedition accomplished. Rather than a single observation pass across one portion of the floor, the Limiting Factor's multiple descents allowed researchers to map the 3 distinct subbasins within Challenger Deep in greater detail than had been possible before, confirming their depths and refining the understanding of the floor's topography at a resolution that previous instruments had not achieved. By the end of the 5 Deeps expedition and the subsequent research dives conducted with the Limiting Factor in the years following, the vehicle had completed more dives to full ocean depth than all other manned submersibles combined. This accumulation was not a record pursued for its own sake, but a consequence of the vehicle's design. It had been built to go there repeatedly, and it did. Each descent added data. Each return to the surface brought back sediment, water, or biological samples that extended the picture researchers were building of the deepest place on Earth. The specific measurement that the 5 Deep survey returned for the deepest point within Challenger Deep, 10,925 meters, with an uncertainty of approximately 11 meters on either side, was the most precisely determined figure yet produced for the trench's maximum depth. The 2010 multi-beam sonar survey had placed the deepest point at approximately 10,935 meters. The differences between these figures are small, and the methodology of each survey was slightly different, operating from different vessels with different instrument configurations and different tide correction approaches. What both surveys agreed on was the structure of the floor, three separate basins, each exceeding 10,900 meters, arranged from west to east across the interior of Challenger Deep. Don Walsh, who had been 28 years old on the day in January 1960 when the Trieste reached the bottom, descended to the floor of Challenger Deep again aboard the limiting factor during the Five Deeps expedition, roughly 59 years after his first visit. The floor he saw on the second descent was in its physical character the same floor he had seen through the Trieste's viewport in 1960, the same pale sediment, the same cold, still water, the same absolute darkness beyond the vehicle's lights. The technology surrounding him was entirely different. The instruments recording the environment were more numerous and more precise. The ability to move across the floor, to direct the cameras, to collect targeted samples, was incomparably greater than what the Trieste had offered. The floor itself had not changed in any way that the human timescale could register. The chain of descents from 1960 to the present connects several generations of engineers, scientists, and divers through the same physical destination. Each expedition approached Challenger Deep with different equipment, different questions, and different capacities for recording and retrieving what it found. The Trieste could reach the floor and remain there briefly, with two people in a small sphere looking out. Keiko could operate alone for extended periods, collecting samples from a vehicle with no human occupants at the site. Cameron could spend 3 hours on the floor, piloting, observing, deciding in real time where to direct the cameras. The limiting factor could go down and come back, and go down again until the floor of Challenger Deep had been mapped across its full extent with instruments sensitive enough to distinguish its three basins in detail. What accumulated across these visits was not a single discovery, but a growing familiarity with a specific place. The deepest point in the ocean became, through repeated human attention, a location with a history of being visited, a place that had been seen, sampled, documented, and returned to. The sediment surface that Walsh and Picard had looked at through the Trieste's viewport in 1960 was the same sediment surface that Keiko's cameras had recorded in 1995, and that Cameron had crossed in 2012, and that the limiting factor had mapped in 2019 and after. The floor was continuous. The visits were a series of moments of human attention distributed across decades, each one adding to a picture that none of them alone was sufficient to complete. The engineering required to send a vehicle to full ocean depth and retrieve it intact represents a particular kind of difficulty. The primary challenge is pressure. At 10,900 meters, the hydrostatic pressure is sufficient to compress almost any material that contains air or any gas-filled cavity. The Trieste's observation sphere was cast steel, thick enough to resist deformation at that pressure. With a single viewport made of extremely thick conical glass, the glass itself tapered in a shape that allowed the pressure outside to drive it more firmly into its conical seat, the deeper the vehicle went, rather than pushing it inward. The Deep-Sea Challenger used a similar pressure vessel approach, though its construction incorporated modern materials and more precise manufacturing tolerances. The limiting factor's pressure sphere was built from titanium, a material with a favorable ratio of strength to weight, machined to close tolerances, and tested repeatedly at simulated depth pressures before any diver entered it for an actual descent. The fiber optic tether that connected Kaiko to its support ship represented a different kind of engineering problem. The tether had to transmit data and power through more than 10 kilometers of water while remaining strong enough to resist the forces acting on it during deployment. The weight of the cable itself, the drag of currents in the upper water column, the stress of recovery operations at the surface. The loss of Kaiko in 2003 was a consequence of conditions at the surface, rough weather and wave action that placed forces on the tether beyond what it could sustain, rather than any failure at depth. The vehicle itself, operating at 10,000 meters, was functioning normally when the connection to the surface was severed. The limiting factor carried no tether in the conventional sense. It descended and ascended freely, to maintaining acoustic communication with the support ship above through a system that transmitted compressed data through the water column, a channel with far less bandwidth than a fiber optic cable, but one that required no physical connection between the vehicle and the surface. The trade-off was information rate. The acoustic link could send and receive commands and status data, but not the high-definition video that a fiber optic tether could carry in real time. Footage from the vehicle's cameras was stored on drives inside the pressure vessel and retrieved when the vehicle surfaced. These engineering details are not incidental to the history of exploration, but integral to it. The questions that could be asked at any given point in the exploration of Challenger Deep were shaped by what the technology of the time could carry to the bottom and bring back. The Trieste could carry 2 people and whatever they could observe through a small viewport. Kaiko could carry cameras, manipulator arms, and sample collection equipment, operated by pilots at the surface through the tether. Cameron could carry scientific instruments and make real-time decisions about their deployment. The limiting factor could carry 2 people and a full suite of instruments, go to the bottom repeatedly, and bring back water and sediment samples, as well as high-resolution mapping data from its sonar systems. The shift from manned to unmanned and back to manned again across these expeditions was not a single trend, but a reflection of different priorities and capabilities at different moments. Unmanned vehicles can be built lighter and can operate longer without life support constraints. Manned vehicles bring the capacity for real-time judgment, the ability to respond to unexpected observations in ways that a remotely piloted system, operating across a signal delay with limited sensory feedback, cannot always replicate. The deep-sea exploration programs of different nations and institutions made different choices about this trade-off, and the record of those choices is visible in the history of who reached the bottom of Challenger Deep, with what, and when. What is consistent across all of these visits, from Walsh and Picard to the 5 Deeps program and beyond, is the patience required. The ocean does not cooperate with urgency. Reaching the floor of Challenger Deep from the surface takes hours. The descent of the Trieste took nearly 5 hours. The limiting factor's descents took around 4 hours in each direction, with the time on the bottom varying depending on the objectives of the dive. Each expedition required weeks of ship time in the Western Pacific, substantial logistical preparation, and the coordination of engineering, science, and operations teams, whose work spanned years before any vehicle entered the water.
The Titsnes to the Darissamaten Salman's region of the ocean was itself a commitment of 3.5 years, a voyage that departed in 1872 and returned to England in 1876, having covered a distance comparable to crossing the Atlantic more than 17 times and having collected enough data to occupy the scientists who worked on it for decades afterward.
The report produced by the Challenger expedition ran to 50 volumes when it was finally published, beginning in 1880 and not completed until 1895. The depth measurement taken in March of 1875, which started the chain of inquiry that eventually led to the Trieste dive and everything after, was one data point among thousands gathered on that voyage. It was not identified at the time as the most significant measurement of the expedition. Its significance emerged later as subsequent surveys confirmed that the region sounded in 1875 was indeed the deepest part of the ocean. The 1875 sounding and the 1960 dive are separated by 85 years. The 1960 dive and the 2019 Five Deeps expedition are separated by 59 years. Within these intervals, the technology of measurement changed more than the place being measured. The water above Challenger Deep in 2019 was the same water in its physical character as the water above it in 1875 and 1960, cold, dark, deep, pressurized, and largely the same temperature throughout its lower kilometers. The floor of the trench accumulated sediment at the same slow rate across all these decades, receiving the same slow rain of organic material from the surface, the same gradual accumulation of fine particles drifting down through kilometers of water. The human expeditions that arrived at intervals across this period were brief events in the life of a place that measures its own history in millions of years. After the Five Deeps expedition, the DSV limiting factor continued to be used for deep-sea research operations, returning to Challenger Deep and other Haddle sites as part of ongoing scientific programs. The pattern of accumulation that the expedition had established, repeated descents to the same location, each one contributing additional data to the shared picture, was carried forward into subsequent research. The floor of Challenger Deep, which had been visited twice in the entire 20th century by vehicles carrying humans, had been visited many more times in the first 2 decades of the 21st. The Trieste observation sphere, in which Walsh and Piccard made their descent in 1960, is preserved today at the Navy Museum in Washington, D.C. It is a small object, significantly smaller than it appears in photographs taken beside the full bathyscaphe. The viewport is thick and slightly yellowed and narrower than most people expect. Looking at it gives a reasonable sense of what the 2 men inside it could actually see of the floor of Challenger Deep. Not much, and not clearly, but enough to know they were there, on the bottom, at the deepest point in the ocean, in a vessel that was holding together exactly as it was designed to do. The deepest point in the ocean has now been visited enough times that the word routine is nearly applicable, not because the dives are without difficulty, but because the limiting factor's repeated descents had reduced the act of reaching the floor of Challenger Deep from a singular event to a repeatable operation. This is a change of kind, not just of degree. The first dive was an act of first arrival. The second dive, 35 years later, confirmed that the floor was accessible and observable. The dives that followed added resolution and duration. The limiting factor's descents added frequency. Across all of them, each one contributing its layer to the accumulated record, the deepest place on Earth became steadily better understood, not fully, not finally, but more than before, and with the quiet confidence of a place that has been returned to enough times to begin to feel known. The DSV limiting factor has surfaced from the floor of Challenger Deep more times than any other vessel in the history of the ocean's exploration, and more. Each time it rose through the water column, through the deep black of the Hoddle zone, past the cold dark of the abyssal, into the fading blue of the upper water, it brought back data from a floor that had been accumulating sediment since long before any human being existed to think about it. Each dive added one more descent to the record. Each surface recovery closed one more loop between the deepest point on Earth and the ship waiting above in the warm Pacific light. The record now stands at more visits than all other manned submersibles to full ocean depth combined, and the floor below continues to receive its slow, steady rain of particles from the water above, as it has for as long as the trench has existed, unhurried by the visits and unchanged by the attention. The sediment floor of Challenger Deep, seen through a camera light mounted on an ROV, looks almost featureless, pale, still, extending outward in every direction until the light gives out and the darkness takes over completely. There is no visible movement, no obvious texture, nothing that catches the eye the way a fish or a worm or a cluster of tube structures might. But the surface is not bare. Stretched across that pale sediment, so thin it reads at first as a slight change in color, is a living mat of bacteria and archaea, organisms so small that tens of millions of them occupy a single cubic centimeter of material. They are processing organic matter in cold, pressurized darkness at approximately 11 kilometers below the ocean's surface, and the rate at which they are doing so turns out to be higher per unit area than in almost any other seafloor environment at comparable depths. The floor of the deepest trench on Earth is not quiet in any biological sense. It is just quiet at a scale the eye cannot resolve. What arrives at that floor has traveled a long way. Particles of organic material, fragments of dead organisms, fecal pellets, aggregates of cellular debris, loosely called marine snow, drift downward from the sunlit zone above through thousands of meters of cold water. Most of what sinks in the open ocean gets consumed and recycled long before it reaches the bottom. But the Mariana Trench is shaped in a way that changes that calculation. Its narrow, elongated form acts as a kind of collector. Material settling toward the trench from the surrounding abyssal plain gets funneled inward and downward by the trench walls. What arrives at Challenger Deep is not just what fell from directly above. It is an accumulation from a much wider area of ocean surface, concentrated by topography into a relatively small receiving basin at extreme depth. The result is a sediment surface that is unusually rich in organic carbon for its depth. And where there is organic carbon in the ocean, there are microorganisms to process it. Piezophilic bacteria, organisms that not only tolerate, but require high hydrostatic pressure to function, maintain their cell membranes through a particular biochemical strategy. At the pressure found in Challenger Deep, which reaches approximately 1,086 atmospheres, the lipid bilayer that forms the outer membrane of a bacterial cell would ordinarily become rigid and effectively non-functional. Membrane proteins embedded in that bilayer, which must move laterally through it to carry out essential cellular tasks, would slow and eventually stop. The cell would not be crushed in any dramatic sense. It would simply cease to work. Piezophiles address this by maintaining membranes that are unusually rich in unsaturated fatty acids. The double bonds in those fatty acid chains introduce kinks in their molecular geometry, small bends and angles that prevent the tight, ordered packing that leads to rigidity. At pressures that would turn an ordinary bacterial membrane into something resembling a solid rather than a fluid, the unsaturated chains of a piezophile's membrane remain in a phase that allows proteins to move freely through them. The cell stays functional. What looks from the outside like an extreme environment looks from the inside of that membrane like ordinary conditions. This is not a fragile workaround. It is a stable, heritable adaptation found across multiple lineages of deep-sea bacteria, some related to each other and some not, suggesting it has evolved independently more than once in response to the same set of constraints. The chemistry is not unusual in its components. Unsaturated fatty acids are common across biology, but the proportions found in Haddle bacteria are distinct enough to be diagnostic. A membrane retrieved from Challenger Deep sediment and examined under a microscope has a measurably different composition from one retrieved at 1,000 meters, or at the surface. The deeper the organism lived, the more pronounced the difference tends to be. The archaea present in Challenger Deep sediment operate under the same pressure constraints, but often address them differently, through distinct membrane chemistries involving ether linkages and branched isoprenoid chains rather than the ester-linked fatty acids common in bacterial membranes. Archaea and bacteria are not closely related despite their superficial similarity. They diverged so long ago that their membrane chemistries evolved independently, and both have arrived at workable solutions to the same problem of maintaining fluidity under high pressure. The floor of the Mariana Trench is, among other things, a place where the two deepest branches of cellular life have independently solved the same biochemical problem and gone on living together in the same few centimeters of sediment. In 2013, a study led by Ronnie Gludd of the University of Southern Denmark and published in Nature Geoscience measured oxygen consumption rates in Challenger Deep sediment and compared them to rates in surrounding abyssal sediments at shallower depths. The expectation going into that work was not unreasonable. Deeper sediments, with less organic input and more extreme conditions, might be expected to show lower microbial activity than shallower ones. What the measurements showed was the opposite. Oxygen consumption in the trench sediments was significantly elevated above what the surrounding plain could account for. The microbes at the bottom of Challenger Deep were respiring more actively, not less than their counterparts in the wider abyss around them. The explanation that Gludd and colleagues proposed connects back to the funneling effect of the trench's topography. If more organic material is being delivered to the trench floor than to the surrounding plain, then the organisms living there have more to work with. More food means more respiration. More respiration means faster oxygen depletion in the upper sediment layers. The oxygen microprofiles that Gludd's team measured, tiny sensors reading dissolved oxygen concentration at millimeter intervals downward through a sediment core, showed a steep drop in the uppermost centimeters. The signal fell rapidly in the zone where microbial activity was highest, then leveled off as oxygen became limiting, a pattern consistent with a community working at or near the limit of what available food and terminal electron acceptors could support. The instruments that produced those measurements are small enough to hold in one hand. The sensor tip that actually takes the reading is narrower than a sewing needle. Setting one of those sensors into a sediment core retrieved from the floor of Challenger Deep and watching the oxygen signal step downward at millimeter intervals is, in physical terms, one of the stranger acts in oceanography. A tiny instrument from a ship making a measurement about what is happening 11 kilometers below in a tube of mud that was a few minutes ago at the bottom of the deepest hole in the ocean, now sitting on a laboratory bench in ordinary air. What those measurements tell, taken together and examined against the context of the surrounding plain, is that the Mariana Trench is not a place where life has found a marginal, barely surviving foothold. It is a place where life, at the microbial scale, is relatively thriving. The same feature that makes it the deepest place on Earth, the narrow, walled basin that plunges below everything else, is precisely what makes it a better than average site for microbial metabolism at great depth. Among the organisms living on the sediment surface of Challenger Deep, some of the most visible to a camera, visible in the sense that they can actually be seen as distinct forms rather than inferred from measurements, are the xenophyophores. The name requires a moment to settle in. They are foraminifera, a group of single-celled organisms with a long fossil record and a wide distribution across the ocean floor, most of them small enough to be microscopic. Xenophyophores are foraminifera that have, over evolutionary time, grown very large. A xenophyophore found at approximately 10,641 meters depth in the Mariana Trench can reach up to 10 centimeters across. 10 centimeters for a single cell, not a colony of cells acting together, not a multicellular organism organized into tissues and organs. One cell spread across a space roughly as wide as a human hand. The cell does not look like what most people imagine when they hear the word cell. It has no obvious nucleus visible to the naked eye, no differentiated internal regions, nothing that reads as a body plan. What it has instead is a test, a shell-like structure built not from a material the organism secretes, but from mineral particles and foreign debris gathered from the surrounding sediment and bound together by cytoplasm. The xenophyophore is, in a structural sense, an organism that has wrapped itself in the environment it lives in. Its test incorporates sediment grains, sponge spicules, shell fragments, whatever the surrounding floor provides, assembled into a lattice structure that can hold the cytoplasm within it and protect it, loosely, from physical disturbance.
What this organism is doing at 10 centimeters across, at 11 kilometers depth, is not something the xenophyophore can be said to have decided. It grew to that size because the lineage that gave rise to it has been growing to that size for a long time, and the conditions of the deep ocean floor, stable, cold, low current, with steady if slow organic input, do not penalize large, slow, single-celled growth the way shallower, more energetic environments might.
The giant size may also confer a benefit in terms of cytoplasmic surface area available for engulfing organic particles from the sediment, though the precise energetics of xenophyophore nutrition at Hadal depth are still being worked out. What is clear is that they are present at full Hadal depth, documented by camera at 10,641 meters, and that their presence there is consistent with a wider pattern in which the deep ocean has produced some of the largest single cells ever recorded anywhere on Earth. The deep sea does not, as a general rule, shrink things. It produces some of the largest, slowest, oldest organisms in biology, and the xenophyophores fit that pattern exactly in their unhurried, architecturally assembled way. The sediment that xenophyophores grow on and incorporate into their tests is itself a record of what has been arriving at the floor of Challenger Deep over a very long time. A sediment core retrieved from that floor, a tube of material pressed into the seafloor and carefully extracted, preserving the layered sequence of material that has accumulated over years and decades, is, in one sense, a record of the surface ocean, going back as far as the core is long. Each layer was once the floor's surface. Each layer has its own assemblage of organisms that settled into it, were buried, and either persisted as viable cells or left their chemical traces as they decomposed. Metagenomic analyses of Challenger Deep sediment cores approaches that sequence DNA extracted directly from the sediment without first culturing any organisms have identified thousands of distinct microbial taxa in single cores. Among those thousands, a significant fraction belong to lineages with no close relatives in any database. They are not species new to science in the sense of being slightly different from a known relative. They are lineages far enough removed from any cataloged organism to suggest long periods of isolated evolution in Hadal conditions, genetic sequences that appear in the sediment of the deepest trench, and nowhere else that has been systematically sampled. What that isolation means, in evolutionary terms, takes a moment to consider. If a microbial lineage has been living in the Mariana Trench for long enough to diverge substantially from all other known life, then the trench is not merely a place that life tolerates. It is a place that has shaped life in its own direction, producing organisms adapted not just to high pressure, but to the specific combination of conditions found only there. That particular pressure, that particular temperature, that particular pattern of organic input, that particular chemistry of the surrounding water and sediment. The Haddle Zone has been a consistent environment for a very long time, and consistency, in evolutionary terms, produces specialization. What makes those lineages genuinely novel is not only their genetic distance from other organisms, but the functional genes they carry. Metagenomic work on Haddle sediment has identified genes involved in pressure response, in the breakdown of unusual organic compounds, and in metabolic pathways that have not been well characterized in any other environment. Some of those genes have been found in lineages so distinct from familiar bacteria and archaea that their biochemistry is still largely a matter of inference from sequence data rather than direct biochemical measurement. The organisms themselves, extracted from sediment, returned to surface pressure, kept in a laboratory, often do not survive, or survive poorly, which is itself a kind of evidence that they are genuinely adapted to the conditions below, and not simply tolerating them. The microbial mats that cover parts of the Challenger Deep sediment surface are not uniformly distributed. They appear in patches, thicker in some areas than others, their distribution probably reflecting local variation in organic input rates, sediment composition, and the chemistry of the water just above the floor. Where they are dense, the mat layer can be a dark, cohesive film across the pale sediment, dark because the organisms living in it are packed at densities that absorb light differently than bare mineral grains do. Under the lights of an ROV camera, a patch of dense mat has a slightly different texture from surrounding sediment, a faintly cohesive surface where bare sediment would be loose and particulate. The extracellular polymeric substances that bind mat communities together, sticky molecular scaffolding secreted by the organisms within, serve multiple functions. They physically bind the mat to the sediment surface, preventing dispersal by any slow-moving water currents near the floor. They trap organic particles arriving from above, increasing local delivery of nutrients to the organisms in the mat. And they create a microenvironment within the mat itself that can be chemically distinct from the overlying water, lower in oxygen, richer in the products of microbial metabolism, shaped by the community's own activity rather than solely by the chemistry of the water column above. A mat, in this sense, is not just a collection of organisms. It is an engineered environment that the organisms themselves have constructed. The community builds the chemical conditions that suit it and then lives in those conditions, generation after generation, in the cold and the dark at the bottom of the deepest basin on Earth. A single cubic centimeter of dense microbial mat from Challenger Deep can contain tens of millions of individual cells. To put that number alongside the physical scale of the mat, a layer a few millimeters thick, spread across a square meter of trench floor, would contain more individual organisms than there are people on Earth by several orders of magnitude. The number does not lend itself to easy comparison. It simply sits there, requiring no amplification, as an honest account of how much life is present at a scale too small to be directly perceived. Those cells are not passive. Each one is metabolizing, consuming organic compounds, producing waste products, replicating when conditions allow, dying and being consumed by neighboring organisms in turn. The turnover rate at Haddle temperatures and pressures is slower than at the surface. Cold slows reaction rates, and high pressure, despite being manageable by piezophils, still exacts some metabolic cost. But slow is not stopped. The mat is working continuously, day and night, in a place where the distinction between the two is meaningless because no light has ever reached it in any direction from any source. The archaea within these communities include lineages belonging to groups that have been found in other oxygen-depleted, high-pressure environments, certain methane processing lineages, certain sulfur metabolizing groups, certain deeply branching lineages whose metabolism is still being characterized. Their presence in Challenger Deep sediment is consistent with what metagenomic sampling of other Haddle trenches has found, and it suggests that the deep trenches of the world share a core of microbial community composition, even while each one also harbors its own locally distinctive taxa. What the Gludd study and subsequent metagenomic work together suggest is a picture of the Mariana Trench as a place where the conditions that most life would find prohibitive have been converted, over a very long time, into conditions that a specific, highly adapted community of microorganisms finds adequate and in some respects better than the surrounding plain. The pressure that requires specialized membranes, the cold that slows metabolism to a crawl, the darkness that removes any possibility of photosynthesis as a primary energy source. Each of these is a genuine constraint, and each has been addressed at the molecular and cellular level by organisms that have been living in exactly these conditions for longer than the human lineage has existed. The organic matter that reaches the trench floor is not uniformly composed. Some arrives as relatively fresh particles that sank quickly, zooplankton fecal pellets, for instance, which are dense and can sink several hundred meters per day. Some arrives as older, more degraded material that has been partially processed in the water column during a slower descent. Some arrives incorporated into the bodies of larger organisms that died in the water column above and sank to the trench floor entire, what deep-sea biologists call food falls, events that deliver a concentrated pulse of organic material to a small area of the bottom. The microbial community at Challenger Deep processes all of these, but each type of input sustains a somewhat different set of organisms and metabolic pathways. The degraded, refractory organic carbon that dominates much of the input to Haddle sediments requires specialized enzymatic machinery to break down. Some of the novel microbial lineages found in trench sediment cores carry genes encoding enzymes capable of degrading complex organic polymers that most surface organisms cannot readily attack. In a place where the organic material arriving at the floor has already been processed once or twice on its way down, the ability to extract energy from compounds that other organisms have already partially worked over and abandoned represents a real ecological advantage. The Haddle microbiome, in this sense, is not scraping by on what other organisms have left. It is specialized for exactly the kind of material that arrives. The sediment itself holds viable organisms, not just at the surface, but downward through several meters of accumulated material below the surface. A core extracted from Challenger Deep sediment and opened centimeter by centimeter reveals viable cells throughout. Fewer as the core goes deeper, the material older, the nutrient concentrations lower, but present. Organisms living meters below the sediment surface at Challenger Deep exist in conditions even more extreme than those at the surface. No contact with the overlying water, no fresh organic input, sustained only by whatever organic compounds remain in sediment that may have been accumulating for thousands of years. They metabolize very slowly, likely reproduce rarely, and in some cases may represent relic populations, survivors of a former surface community that were buried as sediment accumulated over them and have been persisting, in a kind of extended low-energy existence ever since. That image, a living organism sustaining itself in sediment at 11 kilometers depth, buried under meters of material that accumulated across thousands of years, metabolizing slowly in complete darkness under more than 1,000 atmospheres of pressure, does not require any dramatization to be striking. It is simply what the data, taken carefully, describes. The question of how many distinct species of bacteria and archaea inhabit Challenger Deep does not yet have a settled answer, and may not be answerable in any traditional sense, given how the concept of species works in organisms that reproduce without sexual recombination and exchange genetic material horizontally across lineages. What metagenomic analyses do allow is an estimate of taxonomic richness, the number of distinct genetic signatures in a community, and those estimates from Challenger Deep sediment run to thousands. Thousands of distinct microbial lineages in a single core from a single location in a place that covers an area smaller than many cities. The cold at the floor of Challenger Deep is not the cold of a freezer or a winter morning. It is a cold that has been stable for a very long time, held in place by the enormous mass of cold water above it, water that has been out of contact with the solar-heated surface for years or decades as it circulates slowly through the deep ocean. The temperature at the Hoddle floor sits near 2 degrees Celsius and varies very little seasonally or annually. For the organisms that live there, this constancy is not a hardship to be endured. It is the baseline. Evolution has tuned them to 2 degrees Celsius, the way surface organisms are tuned to whatever their own ambient environment provides. A warm water bacterium placed at Challenger Deep conditions would slow and stop. A Challenger Deep piezophile returned to surface pressure and temperature would fare poorly in the opposite direction. The adaptation goes both ways. The xenophyophores, resting on the sediment surface, are incorporating mineral particles into their tests at whatever pace the local sediment makes available. They move, if move is the right word for what a single cell does when it extends cytoplasm across a substrate, slowly and without any mechanism resembling locomotion. Their lives consist of chemical exchange with the environment around them, ingesting particles, extruding waste, maintaining the chemical integrity of their cellular interior against an outside environment held at 1,000 atmospheres. How long individual xenophyophores live is not well established. Their growth is slow, their reproduction is infrequent. Under the stable conditions of the deep sea floor, there may be no particular pressure to reproduce quickly. A single xenophyophore sitting on the sediment floor of Challenger Deep at 10,641 meters, 10 centimeters across, built from the sediment around it, living at a pressure that would require a specialized vessel for any person to survive, is in one sense a remarkable thing. In another sense, and perhaps the more honest one, it is simply an organism going about its life in the place it has always lived, doing what its lineage has done for a very long time, unaware of and indifferent to the fact that 11 kilometers above it, the ocean surface is warm and sunlit and crossed by ships whose instruments have recently learned to map the floor it rests on. The microbial mats, the piezophilic bacteria, the deep-rooted archaeal lineages, the xenophyophores, taken together, these are not a collection of exceptions or survivors. They are the majority of life in the deepest place on Earth, in terms of both biomass and individual count. Every macrofaunal organism that moves across the trench floor, every amphipod, every worm, every sea cucumber, lives in a world already saturated with microbial life. feeding in part on the organic matter that the microbial community has processed and made available. The visible animals are the minority. The invisible majority is what underlies them and surrounds them and persists long after they have moved on. The metagenomic record from Challenger Deep keeps expanding as sampling techniques improve and as more expeditions return cores and water samples for analysis. Each new dataset adds lineages, adds metabolic pathways, adds evidence of complexity in a community that, seen from the outside as a pale smear of sediment under an ROV light, gives no sign of being complex at all. The process of identifying what lives there is nowhere near complete. The cores taken so far represent a very small fraction of the trench's floor area, and the methods used, however sensitive, do not capture everything present. There are almost certainly organisms in Challenger Deep sediment whose genetic signatures have not yet been sequenced, whose metabolic strategies have not yet been guessed at, whose place in the community is not yet known. That incompleteness is not a failure of the research, it is a property of the place. The floor of the Mariana Trench is large enough and complex enough in its microbial diversity that a complete census of what lives there is probably not achievable with any technology currently available or easily foreseeable. The thousands of lineages already identified represent a working picture, not a finished one. What that picture shows, with enough consistency across multiple studies and sampling expeditions to be considered reliable, is a living community at the absolute bottom of the ocean that is active, diverse, chemically sophisticated, and in some ways better supplied with organic carbon than the surrounding seafloor at shallower depths. The Mariana Trench is not, at the microbial scale, a marginal place. It is a distinct environment that has produced distinct life, shaped over a long time by conditions found nowhere else on Earth, home to lineages with no close relatives anywhere else in the databases that currently exist to compare them against. Those lineages persist in cold sediment, in complete darkness, under pressure that most materials cannot withstand, processing the organic remains of organisms that lived and died kilometers above them and drifted down across years or centuries before arriving at the floor. They process what arrives. They build mats. They maintain membranes tuned to 1,000 atmospheres. They grow, when the chemistry allows, to 10 centimeters across a single cell. They reproduce slowly, live for spans of time that are not well measured, and carry within their genomes the record of a very long adaptation to a very particular place. The thousands of distinct microbial lineages identified in Challenger Deep sediment cores, many with no known relatives anywhere else on Earth, rest in their cold sediment at the bottom of the ocean, each one quietly going about whatever metabolism the surrounding conditions allow, in the dark, in the cold, at depth, as they have been doing for longer than any measurement yet taken can clearly say. A baited lander settles onto the floor of the Mariana Trench in the final few meters of its descent, its frame touching sediment, its camera light casting a pale cone outward into the surrounding dark. And before the silt disturbed by its landing has fully resettled, something arrives at the edge of the frame. Small, pale, moving with the unhurried efficiency of an animal that has been doing this for a very long time. The attractant suspended below the camera has already begun dissolving into the water column, and Hyrandelia gigas has found it. The amphipod is roughly 2 to 3 centimeters long. Its body is segmented, translucent in places, curved slightly like a comma when it rests, though it does not rest for long. Within minutes of the first arrival, more appear, coming in from the surrounding darkness at the edges of the light until dozens of them are working the frame of the bait cage with their small appendages, their antennae sweeping the water in continuous arcs, reading dissolved compounds at concentrations that instruments aboard the surface ship cannot detect. The camera records all of it. The amphipods continue regardless. Hyrandelia gigas is among the most abundant animals at this depth. It belongs to a group called Lysianassoid amphipods, crustaceans built for scavenging, for finding and rapidly processing food that arrives infrequently from far above. At the surface of the ocean, sunlight drives photosynthesis, and photosynthesis drives almost everything that eats. Down here, at 10,000 meters, none of that light arrives. What does arrive is the slow, continuous fall of organic material from the water column above. Dead organisms, fecal matter, aggregated particles, sinking for weeks before reaching the bottom. When something larger arrives, a dead fish, a cephalopod, a piece of marine mammal, the chemical signal it releases spreads outward through still water, and Hyrandelia gigas follows it with a directness that suggests very little is wasted in this environment. Waste at this depth is a resource that has not yet been found. Research by the marine biologist Alan Jamieson found that this amphipod carries something unexpected in its digestive system, enzymes capable of breaking down cellulose from terrestrial plants. Wood, grass, leaf material, the kind of organic matter that arrives in the deep ocean, not from the water column directly above, but from rivers carrying it off continental land masses and eventually into the sea. At 10,000 meters, in an animal 2 centimeters long, a biochemical toolkit has persisted that allows it to process material originating from forests and fields thousands of kilometers away. The amphipod has no way of knowing this. It finds what falls. It processes what it finds. When the bait cage is heavily occupied, the aggregation of Hyrandelia gigas becomes dense enough that individual animals are visible pressing against one another, layered along the mesh, climbing across the bodies of others to reach the attractant more directly. There is nothing frantic in this. The movement is purposeful and continuous, but not hurried. These animals exist in a place where the next food fall might come in hours or might come in weeks, and their physiology has accommodated both possibilities, capable of rapid feeding when something is available, capable of sustained patience when nothing is. The camera light catches their small pale forms in the darkness, and they go about their work entirely indifferent to being observed. The floor of the Mariana Trench, in the areas away from active food falls, is not empty between visits. Something else moves across it, slowly, covering ground that would take a human diver hours to traverse. Holothurians, sea cucumbers, have been observed at depths approaching 10,000 meters in the Mariana Trench, and the word that researchers have used to describe their distribution is not solitary or scattered. The word that has appeared in expedition notes is herds, not a dense, urgent aggregation like the amphipods at a bait fall, but a slower, more dispersed congregation, pale, elongated animals moving across pale sediment, each one processing the floor as it goes. A sea cucumber at this depth is perhaps 15 to 30 centimeters long, soft-bodied, with a mouth at one end, surrounded by feeding tentacles, and a body that moves by slow muscular contraction. It takes in sediment at its anterior end, extracts whatever organic matter and microorganisms are present as the material passes through its digestive system, and deposits processed sediment behind it as it moves forward. The trail it leaves is faint, a slightly disturbed line across the undisturbed floor. At 10,000 meters, In cold water and near complete darkness, this is a viable way to make a living. The sediment here is not poor. It accumulates organic matter from the water column above, funneled by the geometry of the trench toward its lowest points, and what the sediment holds, holothurians extract. The calm of watching them is not the calm of watching nothing happen. It is the calm of watching something happen at the pace it actually happens, a slow animal doing a slow thing, in a place where slowness is not a disadvantage, but a match between the speed of the creature and the speed at which resources arrive. A holothurian that ate rapidly and moved on would find empty sediment. A holothurian that moves at exactly the pace of the floor's renewal of organic content finds, at each step forward, something worth processing. The pace is not accidental. It is the shape of a long evolutionary relationship between the animal and the floor it inhabits. Concentrations of holothurians, dense enough to be called herds, were not what most researchers expected to find at this depth. The expectation had been sparseness, a few animals widely separated, in a place where food was rare and conditions were punishing. The trench has consistently returned a more inhabited picture than that expectation suggested. Not abundant in the way shallow tropical reefs are abundant, but genuinely occupied by animals that have found ways to persist in a place where the water is cold, the pressure is extreme, and the nearest sunlight is 10 kilometers straight up. Beneath the surface of the sediment, where even the holothurians do not reach, the floor contains its own inhabitants. Polyquate worms, segmented, bristled, typically a few centimeters long, occupy the upper millimeters and centimeters of the trench floor, moving through the substrate, feeding on organic particles and microorganisms. They belong to groups with common names like bristleworms, and in shallow water, polyquates are among the most numerous animals in marine sediments anywhere. At Haddle depths, they are still present. The genera differ from their shallow water relatives. The molecular details of how their bodies hold together differ as well. Proteins are not rigid things. The proteins that give animal tissue its structure, collagen, actin, the molecular machinery of the cell, are folded into specific three-dimensional shapes, and those shapes depend on the conditions around them. Temperature affects folding, pressure affects folding. At 1,086 atmospheres, which is the pressure at the floor of Challenger Deep, an ordinary actin molecule would lose its functional shape. The biochemistry that scaffolds a cell would begin to come apart. Polychaete worms living in the sediment at this depth carry versions of these structural proteins that are subtly different from the versions found in their shallow water relatives, modified at the molecular level over evolutionary time in ways that maintain their structure and function under pressures that would denature the standard version of the same molecule. Denaturation in this context means something specific. It means the protein unravels from its functional shape into something closer to a random coil, still present, still made of the same amino acids, but no longer folded in the way that allows it to do its job. A denatured structural protein cannot hold a cell's architecture in place. A denatured enzyme cannot catalyze a reaction. At extreme pressure, ordinary biology begins to fail, not because its chemistry is wrong, but because its three-dimensional form cannot be maintained. What Haddle polychaetes have, in their collagen and their actin and several other structural proteins, are amino acid sequences that resist this unraveling, that hold their shape in conditions that would collapse the equivalent molecule from a worm living in a tidal flat. The modifications are not dramatic. A changed amino acid here, a slightly different arrangement there. Small differences, held across millions of years of selection pressure, that amount to the difference between persistence and impossibility at this depth. The worm moves through the sediment without awareness of any of this. Its bristled appendages, cata, in the technical vocabulary, push against the substrate, and it advances through the upper layer of the floor, processing material as it goes, in cold water under extreme pressure, in darkness that has existed at this depth since long before the worm's lineage arrived here. What it carries in its molecular structure is a record of that arrival, a set of adaptations accumulated gradually as the ancestors of this worm extended their range downward into deeper and deeper water over geological time, each generation surviving a little more pressure. The selection for pressure-tolerant protein variants accumulating across thousands of generations until the modern animal can live at a depth that would kill most of its distant relatives. Further up in the water column, not on the floor, not in the sediment, but drifting or swimming in the dark water of the Hadal zone itself, other animals move at their own pace through their own particular version of this environment. The Mariana Trench is not only a floor, it is a column of water 10 kilometers deep, and different parts of that column hold different residents. Among the animals found in the open water of the Hadal zone, some of the most structurally simple are also some of the most pressure tolerant, and this is not a coincidence. A comb jelly drifting through the water column of the Mariana Trench at Hadal depth has a body that is by mass almost entirely water. Its structure is gelatinous, not soft in the way that suggests weakness, but soft in the way that suggests an absence of the rigid internal structures that create vulnerability to pressure change. Most of the problems that pressure creates for living things come from what pressure does to gas-filled spaces, air pockets, swim bladders, gas bubbles and tissue, and from what it does to proteins and lipids, whose three-dimensional structure depends on conditions closer to the surface. A body made almost entirely of water, with no gas cavities and no rigid framework to be compressed or distorted, experiences pressure differently. The water inside the animal and the water outside the animal are at the same pressure. There is no differential to collapse anything. The comb jelly drifts through the Hadal zone without requiring the elaborate molecular adaptations that a more structurally complex animal would need, because the simpler architecture is, in this environment, more forgiving. This does not make the comb jelly a primitive organism in any meaningful sense. It is as evolved as anything else at this depth. It simply evolved along a different line, one that arrived at a body plan whose properties happen to make extreme depth livable without extensive additional modification. The comb rows that give comb jellies their name catch available light in shallow water and produce iridescent pulses along the rows of beating cilia. In the deep water of the Mariana Trench, where the camera light of a submersible occasionally passes across them, they do the same thing. A brief, quiet flash of refracted light from an animal drifting upward through 10 kilometers of dark water, entirely at ease in conditions that took engineers decades to learn to design machinery for. Sea anemones have also been documented in the Mariana Trench, anchored to substrate where substrate is available. They too are gelatinous in significant measure. Their body wall is soft, their internal structure relatively simple, their column and tentacles holding no gas cavities that pressure would compromise. An anemone at depth extends its tentacles into the water column around it and waits, as anemones everywhere wait, for something to pass close enough to capture. The waiting is not a strategy that works only at the surface. It works at 10,000 meters as well, where the water column above delivers organic material continuously, and where small organisms drifting or swimming through the Hadal zone pass within range of an anemone's extended tentacles, just as they do in shallow water. The anemone does not know the depth. It knows the tentacles, the water, and the slow current of whatever arrives. Among all the animals documented in the Mariana Trench and the wider Haddle Zone, none have attracted more attention than the fish. The expectation for a long time was that fish would not be present at the greatest depths. The pressures were considered too extreme, the adaptations required too extensive. What has been found instead is a group of fish so thoroughly committed to deep water that they exist nowhere else, and whose body plan turns out to be, in several specific ways, excellently suited to the conditions they inhabit. Pseudoleperis swire is a snailfish. It belongs to the family Leporidae, a group with members ranging from shallow coastal waters to depths that now exceed 8,000 meters. The individuals formerly described as Pseudolepori swire in 2017 were collected from the Mariana Trench at depths between 6,000 and 8,000 meters. They are typically 20 to 28 centimeters long. Their bodies are soft and slightly translucent, internal organs faintly visible through pale skin in the lights of a submersible camera, a quality that, in a shallow water fish, might suggest fragility, but here is part of a specific and functional architecture. They have no scales. Their fins are broad. They move through the water column with the easy, unhurried quality of an animal that has no natural predators to avoid at this depth, and no particular urgency in any direction. The most significant adaptation they lack is a swim bladder. In most bony fish, the swim bladder is a gas-filled organ that provides buoyancy. The fish adjusts the volume of gas inside it to remain neutrally buoyant at a given depth without expending energy on constant swimming. At extreme depth, this organ becomes a liability. The gas inside it would be compressed by pressure and would require continuous metabolic work to maintain, and at sufficient depth, the compression becomes incompatible with survival. Pseudoleperis swire does not carry this problem. Without a swim bladder, there is no gas cavity to compress. The fish achieves buoyancy through the low density of its gelatinous tissue and through the specific chemical composition of the fluids its body maintains, a solution that works at depth without requiring the fish to fight against the pressure every moment it is alive. The cells of Pseudoleperis swire and its close relatives carry elevated concentrations of a small molecule called trimethylamine oxide, commonly abbreviated TMAO, which stabilizes proteins against the unfolding effects of high pressure. TMAO is not unique to Haddle fish. Many marine organisms use it. What is notable in snailfish from the deepest trenches is the concentration significantly higher than in fish from shallower water, baking scaled with depth in a way that has become one of the clearest demonstrations that there is a molecular solution to the pressure problem, and that evolution has found it independently in multiple lineages that have made the descent into deep water over geological time. A snailfish at 8,000 meters hovers just above the sediment in the light of a camera positioned by an unmanned lander. Its body is angled slightly downward, pectoral fins spread, moving in small adjustments that maintain its position without apparent effort. It has found the bait. It feeds with the same efficient purposefulness as the amphipods crowding the cage below it, competing with them, in a sense, at the same food source. The two animals separated by evolutionary history, so vast that they share no common ancestor, anything like recognizable, and yet occupying the same small cone of camera light on the floor of the same trench, both having arrived at the same depth by routes so different that the routes themselves are worth sitting with. In 2023, a snailfish related to Pseudoleperis swire was filmed at a depth of 8,336 meters in the Izu Ogasawara Trench, south of Japan. This is the deepest confirmed depth at which any fish has ever been observed. The individual was small, juvenile, likely and pale in the camera light, moving through the water column with the same unhurried quality that characterizes the group. It was not doing anything remarkable in the sense of performing for the camera or behaving unusually. It was a fish at 8,336 meters, doing what fish do, moving, orienting, existing in its environment, with the straightforward competence of an animal whose lineage has occupied this depth range for long enough that the depth is simply home. The record matters because it has a boundary. Below a certain depth, somewhere between 8,000 and 8,500 meters, based on current evidence and theoretical models of TMAO concentration limits, fish may not be able to go. The concentration of TMAO required to stabilize proteins against pressure increases with depth, and TMAO itself, at very high concentrations, begins to interfere with the protein function it is supposed to protect. There is a ceiling, or more precisely, a floor, below which the molecular toolkit available to fish may simply not extend. The amphipods and polychaetes and sea cucumbers of the deepest trenches exist in a zone that fish, for all their adaptability, may never fully enter. The snailfish at 8,336 meters is near the bottom of what vertebrate biology, so far as current understanding reaches, can sustain. This does not make the snailfish less. It makes the 8,336 meter mark the edge of something, a boundary that the animal reached not by accident, but through the accumulated consequence of evolutionary pressure across time, each generation a little more tolerant of depth than the one before it, until a small pale fish arrived at a depth that no fish had reached, and continued going about its existence as if the number itself carried no significance, because to the fish it carries none. Back on the sediment surface, the holothurians continue their slow transit across the floor. Hyrandelia gigas continues to work whatever food source the current conditions present. In the upper millimeters of sediment, polychaetid worms move through the substrate in the cold and the dark. The floor of the Mariana Trench is occupied in the way that floors everywhere are occupied, by a community of animals in various states of feeding, moving, waiting, and existing, each one carrying in its body a set of molecular and structural solutions to the specific conditions of this place that accumulated over time through the ordinary mechanism of individuals that survived and individuals that did not. The picture that has emerged from decades of baited landers, remotely operated vehicles, and sediment cores is not the picture of a barren extremity. It is closer to the picture of a functioning community in a particular and demanding habitat, one where the pressures have selected for specific adaptations, where the food source is concentrated by topography, where the animals present are the ones whose ancestors managed the descent into deeper and deeper water, one generation at a time. The trench is demanding. It is also plainly inhabited. Gelatinous organisms deserve particular attention in this account because their presence at Hoddle depth illustrates something that runs through the ecology of the trench more broadly. The body plan that carries no internal gas spaces is a body plan that depth does not penalize. Contenophores, comb jellies, hydromedusae, siphonophores, and other soft-bodied gelatinous organisms have all been observed in the water column of the Mariana Trench and similar Hoddle environments. Their tissue is, in most cases, made up largely of water, sometimes more than 95% by mass. The pressure at 10,000 meters compresses water only very slightly, and a body that is almost entirely water experiences that compression almost uniformly, without the catastrophic differential between pressurized gas and surrounding tissue that destroys a swim bladder or an air-breathing lung. For these animals, the deep ocean is not a hostile environment that required a long evolutionary campaign to colonize. It is an environment their basic architecture was already compatible with. The gelatinous body plan evolved in shallow water and has persisted there for hundreds of millions of years. Its compatibility with extreme depth is, in a sense, a structural accident, a set of properties that the body plan happens to have, which turn out to have value in an environment very different from the one in which those properties first appeared. A comb jelly in a tidal pool and a comb jelly drifting through the Mariana Trench at 9,000 meters are separated by an enormous distance and a pressure difference of nearly 1,000 atmospheres. They are not very different animals. There is a particular kind of observation that becomes possible when enough expeditions have visited a place, when the baited landers have returned enough footage, and the sediment cores have been examined, and the taxonomic work has been done on what was collected. The observation is that the community of animals present in the Mariana Trench is not random. The specific animals there, amphipods over rigid-bodied crustaceans with gas-filled chambers, soft-bodied sea cucumbers over hard-shelled animals with internal air spaces, gelatinous drifters over fish with swim bladders, snailfish at the upper range of what fish can manage, rather than fish built for surface conditions, reflect a consistent pattern of selection. The trench has filtered for specific properties. The animals present are the ones whose properties passed through that filter. Hirondelia gigas passes through that filter in several ways at once. Its body carries no gas spaces. Its cell membranes are enriched in unsaturated fatty acids that remain fluid under pressure. Its digestive system holds enzymes tuned to the organic matter that reaches this depth, not just fresh marine material, but aged, compressed, chemically altered organic matter that has sunk for weeks from the surface. And it can detect a food source at a distance, orient to the chemical gradient, and arrive at the source efficiently, because in a place where food is scarce and competition from animals less adapted to this depth is essentially absent, the animal that finds the food first has a significant advantage. And Hirondelia gigas has had a very long time to develop the capacity to find things quickly. A baited lander left on the floor of the Mariana Trench for 24 hours accumulates a record of visitation that has, in multiple expeditions, shown the same pattern. First, the amphipods, arriving within hours in large numbers. Then, later, larger animals, holothurians crossing the sediment toward the attractant from greater distances, occasionally a snailfish entering the frame from above. The sequence reflects the relationship between detection range, mobility, and body size. Hirondelia gigas detects at close range and responds quickly, in numbers, because its population density in the trench is high enough that many individuals are near enough to respond. Larger animals travel from further away, but travel more slowly. The sequence at a food fall at 10,000 meters is not random. It is a community interacting with a resource in an order determined by the properties of its members. The polycate worms in the sediment do not appear in the camera footage from baited landers. They are below the surface of the floor, out of frame, but they are there, processing organic material that has settled into the sediment and been buried before the amphipods arrived, living out their slow existence in the upper centimeters of a floor that has been accumulating material for longer than the trench itself has existed in its current form. The worms are part of the community that the camera does not catch, and their presence is known from the sediment cores that have been retrieved and examined in shipboard laboratories, their bristle structures preserved in the sample, their molecular adaptations detectable in the tissue that survives retrieval, the sea anemones anchored where substrate permits extend their tentacles into the water column above the sediment, and wait with the patience that anemones everywhere bring to the act of waiting. Their column may be a few centimeters tall. Their tentacles extend a few centimeters further. At 10,000 meters in cold water with almost no current, they are nonetheless functional, capable of capturing whatever small organism drifts or swims within range, of digesting it, of continuing the slow metabolic existence that their body plan makes possible at this pressure without extensive modification. The anemone at 10,000 meters is not dramatically different from the anemone in a shallow tide pool. The conditions around it are. There is something consistently clarifying about looking at the community of the Mariana Trench as a whole rather than as a list of individual adaptations. Each adaptation, the flexible membrane, the modified protein, the absent swim bladder, the gelatinous body, the TMAO elevated tissue, is interesting on its own. What they share, when held together, is the same basic answer to the same basic problem. The conditions here are specific, and the animals present are the ones whose properties allow them to function within those conditions. This is what every habitat on Earth contains: animals whose properties match its conditions, the match having been shaped over time by the same mechanism everywhere. The Mariana Trench is extreme. The conditions that shape its fauna are more intense, more consistent, and more demanding than almost anywhere else on Earth. The animals that have met those conditions are correspondingly more specifically adapted, their molecular machinery tuned more precisely, their body plans selected more narrowly than animals living in environments where the conditions are less demanding or more variable. But the relationship between the animal and the environment is the same relationship visible everywhere. It is just more visible here because the filter is more severe, and the specificity of what passed through it is correspondingly clearer. Pseudoleparus swirae, hovering just above the sediment in the lights of a deep-sea camera at more than 7,000 meters, is the clearest vertebrate illustration of this. Its soft body, its absent swim bladder, its TMAO-enriched tissue, its broad fins, its pale and scaleless skin, each property is a solution to a problem posed by depth, and the animal carries all of them simultaneously, having arrived at its current form through the same long process of descent and selection that shaped the amphipods on the sediment below it, and the comb jellies drifting in the water column above. The fish does not know what the amphipods know, or what the comb jellies experience. If they experience anything, they occupy the same trench and answer to the same conditions in different ways, their differences reflecting the different starting points from which their lineages began. The long descent into deep water, the floor of the Mariana Trench at night. Though night and day are distinctions the trench has never felt, the darkness there being constant and the light at the surface carrying no information to the seafloor below, holds all of this simultaneously. The holothurians move. The amphipods wait or swarm depending on what the water carries. The polychaetes work through the sediment. The anemones extend their tentacles into the water above the substrate. The comb jellies drift upward through the water column, and somewhere, at a depth that sits near the edge of what fish can reach, a snailfish moves through cold, pressurized water with the unhurried ease of an animal entirely at home in the only world it has ever known. The snailfish filmed at 8,336 meters in the Izu Ogasawara Trench in 2023 was small. Its body caught the camera light for a few seconds before the footage moved on. In those seconds, it was simply a fish, pale, translucent, moving slowly through water nearly 10 times colder than a comfortable bath, under pressure that would collapse a steel drum, at a depth no vertebrate has ever been confirmed to exist below. It showed no sign of distress. It had no reason to. The depth was not an extreme, it was enduring. It was the particular conditions of the place where it lived, and it lived there with the straightforward competence of any animal in any habitat that fits it, continuing steadily through cold water and complete darkness at the very limit of where a fish, by all current understanding, is able to be. A tissue sample sits on a laboratory bench under fluorescent light. It came from a small crustacean, pale, about 2 centimeters long, collected in a baited trap from more than 10,000 meters below the surface of the Pacific Ocean. The instruments running beside it are gas chromatographs designed to separate and identify chemical compounds in a sample by carrying them through a column of heated gas and measuring when each one arrives at the detector. The trace moving across the screen should, if the ocean works the way distance and pressure and time suggest it should, be nearly flat. What it shows instead is a series of peaks. The peaks correspond to polychlorinated biphenyls, PCBs, industrial compounds manufactured primarily between the 1930s and 1970s, banned in most countries after 1979, and still present in the tissue of an animal that has spent its entire life at a depth no human has visited more than a handful of times in all of history. The study that followed from that result was published in 2017 in Nature, Ecology, and Evolution by Alan Jamieson and his colleagues. The finding it reported was specific, measured, and quiet in the way that data is always quiet before the implications of it begin to settle. PCB concentrations in Hyrandelia gygos amphipods collected from approximately 250 meters in the Mariana Trench came in at levels roughly 15 times higher than those found in organisms from the Laho River in northeastern China, one of the most heavily industrially polluted waterways in the world. The comparison is useful, not because the two places are similar, but because the Liaohe River represents a kind of benchmark for contamination, a place where pollution had been documented, measured, and held as an example of what industrial chemistry does to an aquatic system when it enters without restraint. The Mariana Trench had, by the instrument's reading, exceeded it. Hyrandelia gygos is a Lycian ascoid amphipod, a scavenging crustacean belonging to a family of animals adapted for locating and consuming organic matter that sinks to the deep sea floor. Individual animals are typically 2 to 3 centimeters long. They move efficiently, their antennae reading dissolved chemical signals in the water around them, their bodies built for the particular combination of cold and pressure that defines the Haddle zone below 6,000 meters. They are among the most abundant macrofaunal animals in the Mariana Trench. When a baited trap is lowered to the trench floor, they can arrive within hours, converging from the surrounding darkness in aggregations that crowd the camera frame, dozens then hundreds, their small bodies pressing toward the attractant with the organized, unhurried efficiency of animals doing exactly what they were shaped to do. The PCBs found in their tissue were not there because the animals had done anything wrong. They were there because PCBs dissolve readily in lipids, in fats, and the deep ocean accumulates fat-soluble compounds the same way it accumulates organic matter, through settling, through gravity, through the slow and patient convergence of everything that descends from the surface. PCBs were synthesized for their electrical insulating properties and their resistance to heat. They were used in transformers, capacitors, hydraulic fluids, and carbonless copy paper. They do not break down readily in the environment. In water, they bind to particles and sink. In organisms, they concentrate in fatty tissue and pass upward through food webs. Each animal that consumes another accumulates a higher concentration than the one it ate. In the deep ocean, where organic matter funnels into topographic depressions and accumulates over decades, this process has no counterweight. There is no sunlight to drive photodegradation. There is no warmth to accelerate chemical breakdown. There are no currents strong enough to disperse what the trench geometry has drawn inward. The cold, the pressure, and the shape of the basin itself create conditions that are, from the perspective of a persistent organic pollutant, nearly ideal for long-term storage. The same 2017 study found polybrominated diphenyl ethers in the amphipod tissue as well. These are flame retardants, compounds added to electronics, furniture foam, and building materials to slow the spread of fire. They share with PCBs the property of lipid solubility, environmental persistence, and the tendency to move through food webs in increasing concentrations. Their presence in Mariana Trench amphipod tissue confirmed that the 2017 result was not an artifact of a single chemical class. Multiple categories of persistent organic pollutant had reached the most remote location on Earth by the same mechanism: dissolution into particles, sinking, accumulation, and uptake by organisms whose bodies process fat-soluble compounds the same way all lipid-rich animals do, because that is what fat is for. A baited trap descending through the water column of the Mariana Trench takes several hours to reach the floor. During that descent, it passes through 11 kilometers of ocean that grades from warm tropical surface water to cold huddled darkness, from a zone of biological abundance and solar energy to a zone where every calorie that arrives has traveled from far above and taken a long time to get there. The amphipods waiting on the floor of the trench at 10,000 meters are not unusual animals in the sense of being rare or poorly understood. They have been studied for decades. Their feeding behavior, their sensory biology, their digestive enzymes, which, notably, include enzymes capable of breaking down terrestrial plant cellulose, suggesting a diet that includes material of land origin carried to sea by rivers. All of these things are documented. What the 2017 study added was a chemical record of a different kind, not what the animals ate, but what the ocean had delivered to them along with everything else. The question of how PCBs and flame retardants travel from their points of manufacture and use to the floor of the Mariana Trench involves the same physical processes that move any particle through the ocean. Compounds that bind to organic matter, to the bodies of plankton, to fecal pellets, to the steady rain of marine snow that carries the surface ocean downward, descend with that material through the water column. In areas where topographic features concentrate downwelling, as trenches do, the material and its chemical passengers accumulate. The Mariana Trench, which draws organic matter from a surrounding abyssal plain, measured in millions of square kilometers, receives a disproportionate fraction of what sinks in its vicinity. What concentrates the food also concentrates the pollutants carried in the food. The two processes are not separate. By 2019, a second study had extended the 2017 findings in a different direction. Researchers from Newcastle University, again including Alan Jameson, published results in Nature Geoscience from an analysis of amphipod digestive tracts and trench sediments collected across 6 of the world's deepest ocean trenches. What they were looking for was microplastic particles, fragments of synthetic polymer material less than 5 millimeters in diameter, produced by the breakdown of larger plastic items and by the direct release of small plastic pellets and fibers from industrial and consumer sources. Every individual amphipod tested from the Mariana Trench contained at least one microplastic particle. The result was consistent across all tested individuals. Not a fraction of the sample, Not a majority, but all of them. Microplastics enter the ocean through multiple pathways. Plastic bottles and packaging break apart under ultraviolet radiation and wave action, producing fragments that continue to fragment until the pieces are too small to see with the naked eye, but still present as chemical objects in the water column. Synthetic textiles, fleece jackets, nylon workout clothes, polyester blankets, release fibers when washed, fibers fine enough to pass through the filters of most wastewater treatment systems and enter waterways directly. Plastic pellets used as industrial feedstock spill during manufacture and shipping and wash into storm drains. The resulting particles are buoyant at first, colonized quickly by marine organisms that render them denser, and then they begin to sink. They pass through the sunlit surface zone. They pass through the mesopelagic, where fish and invertebrates feed in the dim middle ocean. They reach the abyssal plain, and some fraction of them, carried by the same particle flux that brings organic matter to the Hadal zone, settle into the trench. The sediment samples from Challenger Deep, analyzed by the Newcastle Group, contained microplastic concentrations of up to 2,200 pieces per liter of sediment, among the highest microplastic concentrations recorded anywhere on Earth. The figure includes samples from heavily urbanized estuaries and coastal zones with direct plastic input. The particles identified in the Challenger Deep sediment included fibers from nylon and from polyethylene terephthalate, the polymer used to make disposable water bottles, and the synthetic fiber known as polyester. They had arrived, as everything arrives, at the floor of the Mariana Trench through the slow, patient process of sinking. A single fiber of nylon is not a large thing, shed from a piece of synthetic clothing during a laundry cycle somewhere on land, a jacket washed in a machine in a city apartment, the rinse water draining into a municipal system, and from there into a river, and eventually the ocean. Such a fiber is finer than a human hair and lighter than anything that feels heavy when held in the palm. It enters the ocean carrying almost no momentum. It sinks slowly, moving with currents, intercepted perhaps by the bodies of small animals, released, settling further. The descent from the surface to the floor of the Mariana Trench at more than 10,000 meters takes months. The fiber arrives, if it arrives, in a place of absolute cold and absolute darkness, and it settles into sediment that has been accumulating since long before any synthetic polymer was first produced in a chemistry laboratory. It does not degrade. Cold temperatures and the near absence of oxygen in deep trench sediments provide essentially no conditions under which polyester or nylon break down at any measurable rate. The fiber rests. During the solo dive to the floor of Challenger Deep in 2012, James Cameron's cameras recorded the sediment surface at 10,908 meters. In the lights of the submersible, the floor appeared pale, fine-grained, and nearly featureless in most directions. One object was visible that was not sediment, a plastic bag. It rested undisturbed on the floor of the deepest point in the ocean, its material intact, its origin somewhere on a land surface at some point before it entered the water and traveled, over however long it took, to a location that had been visited by human eyes exactly twice before Cameron arrived. Its presence was not exceptional. It was consistent with what the sediment data and the amphipod tissue data would later confirm in more systematic terms. The bag was simply the most visible instance of a process that was already complete. The connection between the surface world and the Hadal floor was not new, and it was not theoretical, and it was not small. The mechanism that makes the Mariana Trench a biological hotspot, the funneling of organic matter from a vast surrounding area into a concentrated topographic depression, operates without discrimination between what is nutritious and what is inert. A trench that collects the bodies of dead animals, the fecal pellets of krill, the cells of decomposing phytoplankton, and the fragments of marine snow also collects whatever has dissolved into or adhered to those materials during their descent. The convergence is physical. Gravity does not distinguish between a lipid-rich copod and a lipid-soluble PCB molecule that has attached itself to the copod's body. Cold, darkness, and the shape of the basin trap, both with equal patience. Herondelia gigas does not experience any of this as an intrusion. The amphipod's antennae detect dissolved compounds in the water, molecules that indicate the presence of food, that orient the animal toward a source of nutrition in the surrounding darkness. Whether those molecules are accompanied by others of industrial origin and carrying no nutritional value is not a distinction the animal's sensory system was shaped to make. It moves toward the food fall. It feeds. It carries in the fatty tissue of its small pale body a chemical record of the surface world that extends back decades to the years when the compounds were first manufactured, when they first entered waterways, when they first crossed the boundary between human industry and the open ocean. The record is involuntary. It is simply what the animal absorbed in the process of eating what the trench provided. The persistence of organic pollutants in deep trench sediments is a consequence of the same conditions that make the Hadal zone extreme by any measure applicable to biology. Cold temperatures slow all chemical reactions, including the oxidative and microbial processes by which organic compounds are broken down in more temperate environments. The near-anoxic conditions in the deepest sediment layers, where oxygen, consumed by microbial respiration in the upper centimeters, has been depleted before it can diffuse further, remove the oxidative pathway almost entirely. The compounds that settle into trench sediment under these conditions are, in any practical sense, archived. They do not disperse. They do not break down at rates that would reduce their concentration over the time scales relevant to any living thing. They accumulate in layers alongside the organic matter and microbial communities and mineral particles that constitute the sedimentary record of the Hadal zone. A sediment core retrieved from the floor of Challenger Deep is a layered object. Its uppermost centimeters hold material that arrived recently, the past few years, the past few decades. Deeper layers hold material that arrived before that, and further down, material that was settling at the floor of the trench before any of the compounds now found in the upper layers were first synthesized in a chemistry laboratory. The transition from pre-industrial to industrial era sediment is not marked by a line or a color change. It is recorded in the chemistry of what is there, in isotope ratios, in compound profiles, in the presence or absence of particular molecules that did not exist in the ocean before specific dates in the 20th century. The 200 microplastic particles per liter found in Challenger Deep sediment are, in this sense, a stratigraphic marker, a boundary layer, as legible in its way as the iridium-rich layer that records the end of the Cretaceous, but formed not by an asteroid, but by the accumulation of choices made about materials and their disposal at the surface of the world. None of this stopped the amphipods. The animals that were collected in baited traps at 10,250 meters and analyzed for PCBs were alive when they entered the trap. They were active, functioning, feeding as efficiently as their species has fed at these depths for as long as the species has existed at these depths. Their tissue carried industrial chemicals and concentrations comparable to organisms from the most polluted rivers in the world, and they were going about their scavenging existence without any apparent departure from the behavior documented in animals from the same location, before any chemical analysis of their tissue had been conducted. Whether the PCBs in their tissue are without biological consequence is a separate question, and an open one. What the study established was that the compounds were there. What they do to an amphipod's biochemistry over its lifetime, across generations, in combination with the other compounds also present, that is a question the data does not yet answer. The same is true of the microplastic particles found in digestive tracts. An amphipod that ingests a nylon fiber while feeding on organic matter at the trench floor does not process the fiber. It passes through or lodges in the gut, neither digested nor expelled in the normal course of feeding, at least in cases where it was found in the preserved material examined in the Newcastle study. What mechanical or chemical effect plastic particles in the digestive tract have on organisms adapted to the specific nutrient composition of Hadal food falls as not fully characterized. The finding documents presence. The implications of presence are a larger and slower question that research is still working through, at a pace appropriate to how recently the methods for asking it became available. The 6 trenches from which amphipod samples were collected for the 2019 microplastic study included not only the Mariana Trench, but also several of the other deepest trenches in the Pacific and Indian Oceans. Across all of them, microplastic particles were found in the digestive tracts of the animals tested. The result was not specific to the Mariana Trench or to its particular geography. It applied broadly to the Hadal zone as a category, to the general class of deep topographically enclosed ocean environments below 6,000 meters, wherever they occur. This suggests that the mechanism delivering synthetic particles to the deepest ocean is not a local phenomenon driven by the proximity of the Mariana Trench to particular pollution sources, but a property of how particles move through the ocean at large, concentrated by trenches wherever trenches exist. The ocean's surface, measured in area, covers most of the planet. Its upper layers receive sunlight, absorb carbon dioxide, generate oxygen, and host the photosynthetic organisms that form the base of nearly all marine food webs. What happens at the surface does not stay at the surface. The biological pump, the process by which organic matter fixed in the sunlit zone sinks through the water column, carrying carbon and nutrients toward the seafloor, operates continuously, connecting the warmth and light of the surface ocean to the cold and dark of the Hadal zone through a slow, steady exchange of material. It is the same process that sustains Hirondalia gigas, that feeds the holothurians moving across the sediment floor, that supports the microbial communities processing organic matter in the upper centimeters of Challenger Deep sediment. It is also the process that carried the PCBs, the polybrominated diphenyl anthers, and the nylon fibers to the same destination. The trench does not distinguish between these categories of input. Its geometry and its physics, the funneling effect, the cold, the pressure, the stillness of the water near the floor, apply equally to everything that arrives. An amphipod's body does not distinguish either. It processes what it finds. The biological pump and the pollutant sink are the same physical mechanism, running on the same gradient, delivering the same material to the same place. The connection is not a metaphor. It is a consequence of how water moves and how particles settle and how the shape of the ocean floor determines where they collect. On the sediment floor of Challenger Deep, at this moment, Hirondella gigas is moving. The darkness is complete and has been complete. At this depth for the entire existence of the species, the temperature is just above freezing, as it has been for as long as there has been a trench here to hold the cold. The pressure is approximately 1,086 times the pressure at sea level. and every cell membrane in every animal at the floor has been shaped by evolutionary time to remain functional under that pressure, to keep the lipids fluid and the proteins folded and the chemical reactions of living things proceeding at the rate required to sustain life. The amphipod's antennae are moving through water that carries dissolved in it traces of the organic compounds released by whatever last settled here, food, or the promise of food, or the chemical signal that the two are indistinguishable from at 10,000 meters in the dark. In the fatty tissue of those small pale bodies, the PCBs are present. They have been there since the animal last ate. They were in the food, and they are now in the animal. And when the animal is eventually consumed by something else, another amphipod, or a snailfish, or a polychaetid in the sediment, some fraction of the compounds will move into that organism's tissue and remain there. The pathway does not terminate at any particular point in the food web. It follows the organic matter wherever the organic matter goes. The trench that collects everything also holds everything. The researchers who measured the PCB concentrations did not describe the result as a disaster. They described it as a finding. The data they published showed what was present, at what concentration, in what organism, at what depth. The instruments had been precise, and the sampling had been systematic, and the comparison with the Liahe River concentrations had been made to give the number scale and meaning, not to dramatize it. What the finding required was attention, not alarm, but the kind of clear-eyed attention that comes from reading a table of numbers and recognizing that the numbers are telling a coherent story about how the ocean works and what it receives and what it keeps. The amphipods in the Mariana Trench were not aware of the study. They were not aware of the instruments that had analyzed their tissue samples. They were not aware of the rivers and factories and landfills from which the compounds in their bodies had originated, or of the decades those compounds had spent moving through the ocean before settling into the food web that sustained the animals at the deepest point of the trench. They were aware in the functional sense that an animal with antennae and sensory neurons is aware of the chemistry of its immediate environment, of the water around them, of the gradient of dissolved organic compounds leading toward a food source, of the presence of other animals at the same source, feeding. This is what they were doing before any of the studies were conducted. This is what they continue to do. There is something orderly about that persistence. Not comfortable, exactly, but orderly. The world's surface produces compounds that do not break down, and the ocean receives them, and the particles carry them downward through 11 kilometers of cold water, and they arrive at the floor of the Mariana Trench in the tissue of the animals that live there. The system that does this is the same system that delivers everything else to the same floor: the carbon, the nitrogen, the organic fragments, the marine snow, the slow, steady rain of material from which the entire Hadal food web is built. Nothing arrives at the bottom of the ocean without having traveled through everything above it. The trench receives what the ocean provides. It has no other input. The flame retardants found alongside the PCBs in the 2017 study were present in amounts too small for the instruments to quantify with the same precision as the PCBs, but they were present. Their detection confirmed that the 2017 result reflected a general property of the Hadal environment, rather than a contamination artifact or a consequence of one specific compound class's unusual behavior. Multiple distinct chemical families, sharing only lipid solubility and environmental persistence, had all followed the same route from manufacture and use to the fatty tissue of a scavenging crustacean at 10,250 meters. The route does not require any unusual mechanism. It requires only that compounds bind to organic particles and that those particles sink as they have been sinking into the ocean since before any of the compounds existed. The nylon fiber in the sediment of Challenger Deep is not moving. It settled into position at some point after it entered the ocean, after it was shed from a synthetic fabric into a laundry drain, after it traveled through a wastewater system and into open water, after it drifted through the surface layers and the deep layers and finally arrived at the floor. It will not degrade at any rate that is meaningful against human timescales. The sediment will accumulate around and above it, slowly, a millimeter or a fraction of a millimeter per year, and the fiber will be buried, and then buried deeper, and the layer it rests in will become part of the stratigraphy of the trench, part of the record of what was present in the ocean in the era when polyester first existed. That record is not going anywhere. It will remain where it is for longer than the compounds themselves have existed, and longer than the industries that produce them, and longer than most of the institutions that might someday attempt to understand what the record means. The amphipods do not rest. Hirondelia gigas is a scavenger in a food-limited environment, shaped by millions of years of selection pressure toward efficient detection and rapid exploitation of whatever organic matter arrives at the trench floor. Food falls in the Hadal zone are rare and unpredictable, and the animal's behavioral repertoire is organized around finding them quickly when they occur. The antennae work continuously. The small body moves. The darkness that surrounds this movement is as complete at 10,000 meters as darkness anywhere on the planet. No bioluminescence from the amphipods themselves. No reflected light from above. No ambient glow of any kind. The camera lights of the research lander are the only light source, and they illuminate a small cone of sediment floor where the attractant has drawn the animals together, and beyond that cone is an unbroken darkness that extends in every direction for as far as the trench goes.